Thanks to the meticulous astronomical observations of his colleague and employer Tycho Brahe, Johannes Kepler was able to test several rival hypotheses for how the Sun and the planets are arranged in the solar system, eventually leading to his 3 laws of planetary motion. In 1609, he published the first 2 laws in a book called Astronomia Nova, which focused on the movements of the planet Mars. Mars was something of a conundrum. Its observed motions didn't match any of the proposed models of the solar system, which involved circular orbits. Kepler's first law states simply that Mars travels in an elliptical orbit, with the Sun at one focus of the ellipse. Although he chose to list it first, Kepler only came to this conclusion after figuring out his second law, which says that if you draw a line from the Sun to Mars and wait a fixed amount of time, that line will sweep out a certain area as Mars moves along its orbit. What Kepler noticed was that this area is exactly the same no matter where in the orbit you are. This is often phrased as Kepler's equal area and equal time law, and this law works because Mars doesn't move at a constant velocity. It speeds up the closer it gets to the Sun. So if Mars is approaching perihelion, the point in the orbit nearest to the Sun, it's traveling faster than if it's at aphelion, the point that's farthest away. In the first case, the line connecting Mars to the Sun is very short, but because the planet is moving faster, it covers a lot of distance. In the second case, the line segment is much longer, but Mars also moves more slowly. Either way, the area swept out in a fixed amount of time is the same. Kepler and his contemporaries could see that Mars doesn't move at a constant rate, but they didn't know why. This inverse relationship that Kepler proposed between distance from the Sun and orbital velocity could explain the puzzling observations of Mars' movements, but only if the orbit is an ellipse. A circular orbit would mean no change in distance from the Sun with time, and thus the velocity would be constant as well. These 2 statements, that Mars travels in an elliptical orbit and that its speed varies so that the Mars-Sun line sweeps out equal areas in equal time, were generalized to include all planets in 1621, and they constitute Kepler's first and second laws of planetary motion. The second law, it turns out, is also a consequence of the conservation of angular momentum, which was not a concept known to Kepler in the 17th century. Angular momentum is a measure of the amount of rotational motion in a body or system of bodies, like Mars and the Sun, and in the absence of outside forces, it's a fixed quantity. This implies a trade-off between the distance at which Mars orbits and its velocity, like Kepler noticed. Just as an ice skater spins faster after pulling her arms closer to her body, Mars has to move faster when it gets closer to the Sun. Kepler's statement that the area swept out by the Mars-Sun line is constant is equivalent to the statement that angular momentum is a constant as well. That is to say, that it's conserved.